Hi, welcome to ARISTOTHINK. Let's see another video about physics. This time we're going to see the banked surface with friction, which is, there is a car on a track, but this car wants to go very fast on the curve. So the curve must be inclined so the car can go faster and faster. And this is what we're going to see. And I want to know something. I want to know what is the fastest way this car can go without sliding up. Now, so this is the problem. So this is the inclined plane. I'm going to make the car as a single point. So I'm going to represent the whole mass of the car for each center of mass. That's how we simplify things in physics. It's much easier to work. So this is going to be the weight, mg. Now, there is going to be a normal force perpendicular to the track, like that, and there is friction. Now let's analyze what friction, where is going to be look like. I don't know if I have seen, but there are some tracks. It's almost a wall, it's almost 9 degrees. And it really works. The car goes like that. I don't know how to draw a car. This is the back of the car. The car is going out of the blackboard. It's so steep, it is so steep that the car must go very fast or it's going to fall. In this case, clearly, the car is basically almost falling. So, it must go, there is a minimum speed this car can go without falling. In that case, if we're searching for the minimal speed so the car doesn't slide down, so the friction is up. In our case, it is the opposite. We want to see how fast can this car go without sliding up. You see, because if it goes, in this case, very slow, it can fall. So the friction is up. On this case, the car is going very fast, very fast. So the tendency of this car is to escape to the outside of the curve. So the friction, the car is going in this direction, so the friction is opposite to the force. So the friction is in this direction. So this is going to be the friction force. This is going to be the normal force. Wonderful. Now that we did all this, of course, always start by drawing a free body diagram. It's very important. And I'm going to put the axis. This is going to be the x, this is going to be the y, and this is going to be our free body diagram. Wonderful. Well, this is a bit wonderful. Now we have to start thinking about the components. Just one thing. Somebody might ask me, well, you did not put the mg sign, because some people put mg sign because they said, of course, I heard in my school that when you have an inclined plane, this is alpha, so there is an mg sign here and the normal here. And I said, you put the normal, you didn't put the mg sign. Hey, let's stop. Let's work things through with caution. Yes, we do have the inclined plane. We do. Now, this is the center of the mass of the object. This is the weight, mg. If we decompose mg, we're going to see that we have these components and that components pushing the car against the surface and also pushing the car in this direction. Now, that's why we put this mg sign, and as a consequence of pulling down the car, there is the normal force. But think for a moment. The normal force is a force after the fact that the car is being pushed against the surface. So this force is a true force. This force, it is a component of the weight. But now I'm going to make you see something. Tell me something. If the weight is down, is it possible to have any components in this direction? I don't think so. There isn't. So be careful. Be careful when you are decomposing forces. You might get in a loop and lose yourself. We are trying to find, because we want to know this force to this direction, because this is going to be the centrifugal force. We're trying to find every force that's going to compose our centrifugal force. And remember, centrifugal force is not a force itself. It is just a name of a group of forces. Centrifugal force can be weight, can be friction, can be drag, can be many forces. In this case, centrifugal force is going to be the sum of two forces we're going to see. So we are interested in forces that go in the left direction. But weight, it is completely perpendicular. So weight is not contributing anything to the centrifugal force. So be careful. Continuing. Now let's go to decompose those forces. But before that, we gotta find angles, of course. So let's see. I'm going to put this line here. Now I'm going to put that line up here. Good. Now we are set to go. So let's talk about the normal force. The normal force, there is an up, and this force is going to fight with the weight. So let's, oh, I forgot. First, we gotta find the angle. So let's call this one theta. So if this is going to be theta, this one is also going to be theta. Why? Can you see the z? Remember the z? If this is theta as well. If this is theta, this is theta. I hope you can see this, no problem. Now, I'm going to ask you something more. Look at this right angle. If this is theta, this is the complement of theta. That goes to 90. So if this is theta, this is a complement. Call it alpha, whatever. If this is alpha, now look at this triangle now. First, again, look at this triangle. Normal, normal, and friction. If this is theta, this is the complement of theta. Let's call it alpha. Now look at this right angle here. If this is alpha, this is the complement of alpha, which is theta. I'm going to erase alpha because we're not interested in alpha, of course. Only theta. Good. Now, this component is going to be what divided by the normal force is the cosine. What divided by the normal force is going to be the cosine of theta. Well, it is going to be normal cosine of theta. Agreed? So this force is going to be normal cosine of theta. Now this force. This force is the one that's going to help on the centrifugal force. This one. And this one is n sine of theta. Of course. You can also think like this. Whatever is adjacent to theta is a cosine. Whatever is opposite to theta is a sine. So this is n cosine, n sine. Now, and this n sine is going to help with the centrifugal force to this direction. Now let's talk about the friction force. It might scare you a little bit. I don't know if you have thought about this before, but friction force is going to change normal. Friction force is pulling the car towards the centrifugal force and also towards pressing the car further and further into the track. So it is increasing, let's say, the weight, but for certain it is increasing the normal force. Let's put the forces. So the friction force is this way, so we can decompose into this direction, which is going to be in the direction of the centrifugal force, and there is another component like that, and that is something that is going to change the normal force, because you see it's fighting with the normal force. So this one is going to be, so this is theta, this is theta. So together, adjacent to theta, it is a cosine. So this is going to be the friction times cosine of theta, this force. And this force is going to be what? The friction sine of theta. Wonderful. Now we just have to equate things. Normal. the biggest part is done. Now, I'm going to decompose in the x direction and then in the y direction. On the x direction, of course, you want to know the friction, we want to know the centripetal force in this direction. Who is helping? Who is forming the centripetal force? So, centripetal force, which is mv squared over r, is going to be, wait, there are two forces. One is n cosine. Oops, sorry, is the y, is the x direction, of course. So the first one is this one, n sine of theta. There is another one also helping this centripetal force, which is the friction. Friction times cosine of theta. Wonderful. Now let's see the y direction. Up, there is only one, n cosine. So n cosine of theta is going to be, is being balanced by friction sine of theta plus the weight. You see, we have the weights and these little components of the friction. Wonderful. Why do we need this? Interesting to ask. We need this because we gotta find the normal force so we can apply in here, get rid of the normal force, isolate V, and define the answer. Only this. You see, the problem is not that complicated. You just have to find the free body diagram very well and then just follow. So let's see what N is. So N, oh, be careful. Friction, there is a normal force in here. Be careful. So let's go one more line. So N cosine of theta is equals to, what is friction? Mu N times sine of theta plus mg. So the normal force is going to be, oh, let's put everything, let's carry everything to the left hand side. So n cosine of theta minus mu n sine of theta equals mg. So the normal force is going to be what? I'm going to put in evidence those two and bring down. So this is going to be mg. And here we have the cosine of theta minus, be careful, not losing anything, mu sine of theta. Wonderful. So we just have found the normal force. We are going to use on the x equation. Now let's go there. Nice and easy. So let's talk about x direction. X direction is going to be mv squared over r equals to, now friction is mu n. So before substituting, you're going to see, I'm going to change a little bit this equation. So it's n sine of theta plus, what is friction? Is mu n times cosine of theta. Now we're going to put together n in evidence. So n in evidence is going to be sine of theta plus mu cosine of theta. Wonderful. Now let's get better. Sine. Wonderful. Now I'm going to substitute the normal force. That's why I got the normal force for the y equation. Remember, I need this to put in here, and then I'm going to have everything by mg and theta. So the normal force is nothing else than mg over cosine theta minus mu sine theta. This is mg. This is the normal force, right? So I'm just substitute times sine theta plus mu cosine of theta, and everything is mv squared over r. Of course, I'm going to cancel m. Is independent of the mass, and I'm going to bring r along with here. Cross multiplication, right? Whatever I put r here or there is the same. It's cross multiplication. So v squared is going to be G times R sine theta plus mu cosine of theta divided by cosine of theta minus mu sine of theta. Therefore, V is going to be the square root of G R multiplied by sine of theta plus mu cosine of theta divided by the cosine of theta minus mu sine of theta. That's it. That's our solution. So this is the maximum speed the car can go without sliding. If the car goes faster than this, so friction is not going to hold the car and the car is going to slide up. That's it. Think you have enjoyed, and please, 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 if this helped you somehow, please give it a like. It doesn't cost you anything, and it does wonders to me and to my channel, and also it helps other people find this video. If it was interesting to you, very likely it's going to be interesting to others. How can you help others? Just give the like. So YouTube is going to know that the video is interesting, is not something like garbage, and then it's going to put this on the machinery so other people can find my video. If you don't give the like, my video is going to be lost at YouTube like thousands of others. So please, if that was interesting to you, please give it a like. It's very important for the channel and also important for other people to get in touch with this. Thank you very much. I hope you have enjoyed. Please give your comments below, and I look forward to see you on the next video. Bye bye.